All right, so the first thing we're going to look at is sequences. These you've actually probably seen quite a bit before. A sequence is just a list of numbers. But since we're dealing with the math and the actual calculations, we're going to there's some very specific things we're going to look for in a sequence. So the first thing you see on the screen is these are a bunch of sequences. Actually, each row is the same exact sequence. They're just shown different ways. So A, you have the negative n equals 1 to infinity. You can show it this way. It's the exact same thing. If they don't put where it's from, you're assuming it's from 1 to infinity. That's the general assumption, unless they tell you otherwise. And then you can see here, that's just the set notation method there. B, notice they don't put n equals 1 to infinity. Again, it's assumed. And you can see that in the set notation over here, where the first one's -2/3. It doesn't have to start at 1. They just have to tell you if it doesn't. So as you can see here in C, this one's starting at n equals 3. Because if I plugged in n equals 1 or n equals 2, it wouldn't be a real number. So they have to put that there. And then in the other method, they have to tell you n is greater than or equal to 3. And the set notation, you don't have to necessarily show that because you're showing the actual values there. And in D, you can see this one actually starts at n equals 0. So it goes from n equals 0 to infinity. So in the other parts are the exact same thing. And then this one, they have the n is greater than or equal to 0. So there's just multiple ways to write a sequence, but they all the rules and stuff that we're going to talk about work no matter how you actually have the problem written. All right, now we're going to work with a couple sequences to see how they work and come up with equations and stuff for them. And then we're going to start the actual looking at how if it diverges or converges and those type of things. So the first thing this one wants you to do is come up with the equation or a formula for this function. So when we're looking at a function or a series like this, we want to come up with an equation that's going to come up with all these values. So we want to look at the different things that are going on in the problem. So the first thing we notice is that the sign is switching between each one. So the first one's positive, the second one's negative, the next one's positive, and so on and so forth. So when we're writing that, the first thing we're going to put is if you put -1 to the n plus 1 or n minus 1, you can do it either way actually. What we want to look at that one is we want to make sure that the first one in this case is going to be positive and the next one's going to be negative. So anything to the 0 power would be 1. So that first one's going to be 1. If I plug in 1, if I plug in 2, I'm going to get the -1 to the first power, which will give me a negative. So that's going to give me that correct direction there. The next thing we want to look at is my numerator and my denominator. So if we're looking at the numerator in this case, it's going up by 1, right? So that's +1, +1, and so on and so forth. So we have my numerator is going to be n plus 2. Okay, here comes the inevitable question. Why is it +2 when I said it was going up by 1? Because what's going up there, if you remember when you're looking at like slope-intercept form, the number in front of the n is actually what you're adding. So if it was going 3, 5, 7 like that, it'd actually be 2n plus 2. And that would actually give it, because then the first one would be the 0 value there. Actually, this one's going to be different. 2n plus 1. So it'll give you the 3, then the 5, then the 7. So that's the value that's actually being the one added on the top.
So where does the +2 come from?
Because it's n plus 1 plus 1. Your goal is to get the first term to be 3. So if you think about it, remember we're starting off n equals 1, right? So if my first term is n equals 1, what do I got to add to get 3? And that's 2. So n plus 2 would give you the 3 because you're doing 1 plus 2. N is 2. And the same thing, n plus 2 is going to give you 4. So your goal is to get those numbers up top. And sometimes you literally just have to figure out like what value is going to make that happen.
Okay, so we're basing these equations off of where our starting point is. So if our starting point is not 1, we would have n plus another number.
Yeah, so like if when they're setting it as a set like this, you can make the assumption that you're starting off at n equals 1 because that's the first term. Because n is really standing for the number of the term number that you have. Does that make sense?
Okay, so even in the cases where it tells us our beginning is 3, it's still the first term in the series.
Right. So when you're set, if you're going to create your equation from it, you can create the equation based on it being 1 because it's the first term. If they're giving you that information ahead of time, you don't need to come up with the equation because they have to give it to you. They're never going to give you a set and then tell you it's starting off at term 3. Because actually, if you look back here, even like these down here, notice how this has the 3 in it, this has the 3 in it, this set over here doesn't.
Okay.
So if I gave you this, it wouldn't matter. You'd be able to figure out, okay, that's the first term, the second term, so on and so forth. All right, next part, we got to figure out the denominator. So if we're looking at my denominators, we've got, it's 5, 25, 125. Those are multiples of 5. So it's 5 raised to a power. So it's going to be 5 to the n minus 1 power. Actually, no, I don't even need to do the n minus 1. Just 5n to this one. Because the first term will be 1. So 5 to the n, 5 to the first will give you 5, 5 to the second will give you 25, 5 to the third will give you 125. And so on and so forth. So if they give you a set like this and you're trying to come up with the equation, you're just looking at the pieces to come up with the equation. Now, not all function or not all series can make an equation. So here's a couple examples of sequences that we can actually do some calculations and stuff on, but that do not have an actual equation. So if we looked at the population of the world on January 1st every year, that's not going to have, we might be able to model it, but we're not going to be able to get those exact values. If we let a to the n be the nth digit in E, or if we use pi, if we looked at basically all the values out in pi or E, again, there's no formula to figure those out because they're irrational numbers. It's a series, or it's a sequence in this case. So it's a sequence, we can actually go through and do it, but it's not a simple equation that I can come up with like the one we just did in the last problem. The most famous sequence is the Fibonacci sequence. Fibonacci sequence actually has a formula for it, but it's a recursive formula. It's not an explicit formula. So if we go back and look at this one, this is an explicit formula. I can plug in any value of n I want, and I can find that term. So if I tell you right now to find me the 100th term, you can plug in 100 to that n and find me the answer. Fibonacci sequence, we can't do that. We have to do it as a recursive, which means you need to find every value all the way up to the 100th place to be able to figure it out, because it uses the previous terms to calculate the next term. So Fibonacci sequence is, they show you right there. It's a 1, 1, 2, 3, because it's 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. It uses the previous two terms to find the next term in the sequence. And if anybody actually is wondering, he figured it out based on the breeding habits of rabbits.
How?
He observed rabbits. So basically, rabbits, from what I have read, and if anybody's a biology major, I apologize if this is not completely, because obviously everything varies a little bit, but a pair of rabbits can't have babies until they're 2 months old. So once they're 2 months old, they can actually reproduce. So the first month you have one pair of rabbits, the second month you still have one pair of rabbits. The third month you'll have 2 pairs of rabbits because they will have babies on another pair of rabbits. And then the next month, the first pair of rabbits and the second pair can still reproduce. So you have a third rabbit. And then they basically, the 2 pairs of rabbits can reproduce. That's how you have an explosion of rabbits.
That's not more aggressive than an exponential sequence, is it?
It actually is an exponential sequence. It's not an exponential sequence that you can come up with a specific equation for. But it does grow in an exponential format. All right. So when we're looking at sequences, one of the big things that we want to look at is, does the sequence converge or diverge? So if a sequence, as it's going on and on, starts getting closer and closer to a specific value, then it converges. And that's important to know, because if it converges to a single value, we can use that information. If a sequence gets bigger and bigger and bigger, such as like the Fibonacci sequence, that number is going to get larger and larger all the way up. So that number diverges because it's going to basically go off to infinity, which is kind of where I think you were looking at with like an exponential growth. It's just going to keep going and going and getting higher and higher. So it diverges because it's going to infinity. So almost everything that we're doing from this point forward is we're going to be looking at, does it converge or diverge? That's actually almost all of what chapter 11 is dealing with, is being able to figure out if this sequence, or in case where we're going to the next one, this series converges or diverges. And as you can see here, to do that, we're going to be looking at the limit as n goes to infinity. So we're trying to look at it as big of a number as we possibly can plug in and see, does that go to a specific value?
Wait, so Professor, in terms of, so the first one explains convergence and the other one explains divergence?
No. So basically, they're basically the same thing. So as the sequence goes to the limit, so these say the exact same thing. The limit as n goes to infinity of that sequence goes to an L. Now, the L is either a specific number, if it exists, or it goes to infinity, in which case it diverges. So these are just the same thing. They're both saying the exact same thing. As the sequence goes to a really high level or number, n goes to infinity. So the term value goes to infinity.
Okay.
Since we're dealing with limits, we're going to look at just a quick little refresher of how we deal with limits. We're going to look at them in terms of sequences, but these are the exact same rules that you used way back in Calculus 1 before you actually started doing differentiation. As long as both A and B are convergent sequences, this will work. I can split things. So if it's addition, subtraction, I can split them up and look at them individually. If I have a constant, I can pull it out. If I have multiplication, again, I can split it up. Same thing with division. So I can look at each piece individually. And if I have something raised to a power, I can look at the limit of the original piece and then raise that to the power. So we basically can split things up. And this is going to be helpful because if I can split things up, I won't have to look at the limit of the entire problem. I can look at the limit of the pieces, which will allow me to figure out, does it go to 1? Does it go to 0? Things like that, which is what we're going to look at in a second.
So these properties, I'm not seeing them on the PowerPoint.
They might not be in the PowerPoint. They actually might not be in the PowerPoint, but they will be in this, and I'm going to upload this right after class. I stole the PowerPoints that I posted are literally the exact same notes from the book. I just download them and upload them. And I used to actually use them, but I found that this actually works better. And I think it's a little more informative. So next class, I'm actually the teacher. I probably won't even post those. I'll probably just post these notes.
So how would we come across this, like say in the real world or like engineering world, like specifically will we use this to calculate somewhat of a rate at a how like something like that, or?
So you're going to look at, it's actually more going to be what we're going to talk about after. So when we talk about series, when you're doing like summations of values, when you're looking at like, okay, how does this sequence, if I'm adding up all these values together, does it go to a specific point? Is probably where you're going to be looking at it as. So you might be looking at it as in terms of like a pressure on a thing. It's like, is there an upper limit to the pressure that's going to be on that dam? It's like, and we're looking for that limit. Does it converge to a specific thing? Or as more and more, does it just keep going to infinity and everything's going to crash and burn? That type of thing. Does that make sense?
Yeah, like it's kind of like a if it or like if they won't they kind of thing, right?
Yeah, kind of. It's like, and that's why we're focusing so much on being able to find out if it's convergent or divergent. Because if it's convergent, I can find that value. And then I know I can build things to the specific point because I know it's not going to get bigger than that because it's going to converge to that point. If it doesn't, then I got to look at it in terms of it's going to infinity and what do I need to work with at that point. That's really the difference between convergent and divergent. All right, let's look at a couple. So let's look at the limit of this. Now, you actually have done this problem before. You did this one way back in Calculus 1. Does anybody remember the method the teacher used to find the limit of these problems? All right, let's look at it this way. If I took the limit of n goes to infinity of n, because remember, I can split this all up, right? So I can find the limit as n goes to infinity of n plus the limit as n goes to infinity of 1. What's n going to do as I go to infinity?
It's just gonna continue to get bigger, and so it's the one at the bottom. So it's effectively just gonna become 1 over time.
So that's going to go to infinity, right?
Mm-hmm.
And that's going to go to infinity and 1. So now I have infinity over infinity, which is not 1. Infinity over infinity does not exist. Okay. Because technically it's infinity over infinity plus 1, and that still doesn't exist. So the problem with that is like, this doesn't work. So I need to come up with a strategy of being able to do this. So one of the strategies that you saw was if I take everything and I divide it by the same thing. So if I divide the top and the bottom, so if I take n and I divide it by n, I take n plus 1 and I divide it by n. Did I change my problem? If I divide the top and the bottom by n, still the same problem. But now let's look what happens. So now this problem becomes, what's n divided by n? Is 1, right? And then I have n divided by n, which is 1. And then I have 1 over n. There. Now if I look at the limit of each piece, so the limit as n goes to infinity of 1 over 1 plus 1 over n. I now can do it because the top is going to stay 1 because the limit as n goes to infinity 1 is 1. I'm gonna have a 1 there. And what's 1 over n as it goes to infinity?
It's gonna get closer to 0.
That's gonna go to 0, exactly. So now my limit is 1.
But Professor, you said we're breaking that rule there where n plus 1 is divided by n is not the same as n over.
Yes, it is.
Oh, it is, huh? Oh,
The other direction, it is not. If it was n over n plus 1, I couldn't split it. But you can split the numerator and put the denominator in both numerators.
got it. Thank you.
No problem. So since I did that, now I actually can find the limit of this one. So this limit goes to 1. This rule where we're dividing everything by n, those type of things, that's going to be very helpful when we're doing a lot of these problems. Now this one says, is the sequence convergent or divergent? To determine if a sequence is convergent or divergent, if the limit goes to a specific value, then it is convergent. If it goes to infinity, then it's divergent. So let's see what this one does. So if I took the limit as n goes to infinity of n over the square root of 10 plus n. So we're going to do the exact same thing that I did in the last problem. I'm going to divide the top and the bottom by n. So my top becomes 1. And now if I have square root of 10 plus n over n, what happens when I put that n? Now that n is outside of my square root. If I'm going to put it inside the square root, what's going to happen to it?
Square root of n.
Actually, the opposite. It's going to be n squared.
Oh,
Because if I pull out an n squared, I have an n. So now I have the square root of 10 over n squared plus 1 over n. All right, so my limit, the top is still going to be 1, right? But what's the bottom going to go to? That 10, that's going to be the square root of 0 plus 0, right? Because 10 over n squared, that's going to go to 0. And 1 over n will go to 0 if I do the limit. So this would actually end up going to 1 over 0, which is infinity. So since it goes to infinity, it diverges. Does that make sense? See how these two problems are pretty similar in the setup. One This one converges, goes to 1, and this one ends up diverging.
I'm still a little confused. How is 1 over infinity or 1, like when you go to the 1 over n, like the second line of or the second to last line where we have the square root, how do you get from that? Because isn't 1 over infinity, that would be infinity, right?
Yeah.
I
1
think I'm
over
thinking about this
infinity is-
incorrectly.
So as the denominator is getting infinitely large, the fraction goes to 0.
Oh, I had it the wrong way around. That makes sense. Okay,
Yeah,
because it's getting so small that it's just 0.
Correct. Yeah,
Okay.
exactly.
That makes
That's
sense.
why this method works, because it's basically going to get rid of everything that's going to go to 0 at that point.
Okay, that makes more sense. Thank you.
No problem. All right, the next one. So we want to calculate the limit as n goes to infinity of ln of n over n. So in this problem, if we look at the same concept, if we do the limit as n goes to infinity of ln of n over the limit as n goes to infinity of n, as ln goes to infinity, it's going to infinity. As n goes to infinity, it's going to infinity. So in this situation, again, we have infinity over infinity. But in this problem, I can't just divide by n to solve my problem, because ln of n divided by n doesn't help me. That's what I have already. So I've got to come up with some other method to do it. And actually with this one, what we're going to look at is L'Hopital's rule. The L'Hopital's rule says, if I'm looking for a limit, I can take the derivative of it, of both pieces, and find the limit of that one. What L'Hopital's rule only works though on functions. Hi, buddy. And we have a sequence in this problem, so I can't necessarily do it on the sequence. However, if you look at the top, theorem 3 says that if the limit of the function of x goes to L, then the sequence of x also goes to L. So I can, in essence, change this to a function and do my limit, and it's going to give me the exact same thing as my sequence would have done. So we're basically, all we're doing is changing the n to an x. I'm going to do the same problem. So if I'm looking at the limit of n to infinity of ln of x over x, if I do L'Hopital's rule, I'm going to do the derivative of the top and the bottom. So what's the derivative of ln of x? Derivative of ln of x is
1 over x.
Yep. And then the derivative of x is 1. So the limit of 1 over x is 0. So since that goes to 0, I know the limit of n to infinity of ln of n over n also goes to 0. And that's why somebody said in the last a couple problems ago that, oh, infinity over infinity is 1. And we got infinity over here. And the answer did come out to be 1. And I'm like, it's not always the case, because in this situation, my original problem had infinity over infinity and my limit goes to 0. So it's not always going to go to 1.
And so this converges, right?
Yeah, this is going to
does-
converge.
So does convergence or divergence, does that represent on a graph? For example, if it's a convergence, does that mean two things come together, and divergence, they spread apart?
So convergence, actually, if you're looking at it in terms of a graph, it's almost like a, actually, I can show you real quick. I'm going to show you with just an exponential graph, because that's the easiest one to look at it for this. If we have, actually, we'll just do this. We'll do 1 over x. So this right here, if my function, if my sequence was 1 over x, so it's like 1 over 1, 1 over 2, 1 over 3, 1 over 4, all the way down. Notice how this line gets extremely close to 0, and if I keep zooming out, it's basically going to be 0. That's convergent. Where if I had 2 to the x power, now that one, it's getting increasingly large, that's divergent. Now, here's the situation. So if we look at this one, because this one, if you look at it, it looks like it's converging. But as you keep going bigger and bigger, it keeps getting higher and higher. Like it's not going to a specific number. It's literally just going to keep getting higher and higher. It's getting higher and higher at a very slow rate, but it's still getting higher. Does that make sense?
Yeah, I see what you mean.
So that's basically what we're looking at. Like this one's definitely getting closer and closer to 0. And it never goes below 0. So that's what we're looking at. Actually, this one. So let's look at this sequence. -1 to the x power. Notice there's no graph here. So -1 to the x power only exists on whole numbers, which is why we don't see a graph. So if I make this just integers, I don't know if I can actually do on Desmos, but I got the graph, so I can show you what it's going to look like. So this function, if we look at this is the graph, what it's going to look like. What do you notice is happening with this graph?
It looks kind of like a sine wave, right?
Yeah, but the problem is the values between it don't exist. Because if I did -1 to the 1/2 power, for example, it's an imaginary number. So the values between those points don't exist. That's why it's not actually a graph. Like, and also when we're talking about sequences, we're still talking about necessarily the whole numbers. So in this problem, we don't have to worry about the fractions, but that's why it's not connected like a sine graph. But when you look at it, the values on either side, it just keeps alternating between them or oscillating between those 2 points. So this function is going to diverge because it doesn't go to a single value. It would go to 1 or -1, but it won't go to a single one of them. So we don't really have to do out calculations to figure out this one's divergent. We can look at this one and say, this is divergent. Because it doesn't go to a single value.
So let me ask, does this apply to a quadratic equation where you end up getting a plus or minus answer?
If you get a plus or minus, yeah, if you get more than one value, it's divergent.
Okay.
So yeah, if you get more than one value, it would be divergent in that case. All right, let's look at this one. So now this one's got that -1 to the n power there. However, this one's got divided by n on it. So this function, when we're looking at it, that -1 is telling me what the values are going, like it's telling me the signs are changing. But on a function like this, it could actually still converge. So this is what this function looks like. So if we look here and we see this graph, notice how it's still oscillating, right? It's still going positive, negative, because that's what that -1 to the n power does. But if you look at this, it's getting closer and closer to that 0 line. So this one might converge. We actually have to do the calculation out for it. This one might actually converge down to that 0 point, where the other one didn't. It never got closer and closer to 0. So this one's going to use this theorem right here, which says if the limit of the absolute value goes to 0, then the entire function goes to 0. So if I take the absolute value of this function or the sequence, I don't have to worry about necessarily the sign. If it goes to 0, then the actual other function goes to 0. It does not mean if the limit of the absolute value goes to any other number, that's what the other limit goes to. This only works when it goes to 0. Okay. So I get 3 out of here, it doesn't work. It's got to go to 0. So if I look at the limit of this, so the -1 to the n over n, that's really just saying the limit as n goes to infinity of 1 over n, which we already know goes to 0. So since that goes to 0, the original problem goes to 0. So it converges at 0. Does that part make sense? Now let's look at a sine function. All right, so this one I've got the limit as n goes to infinity of sine of pi over n. Now, if we're looking at sine keeps oscillating, right? So if I was to look at this function, so it was sine of pi over x. So that's what this graph looks like. So we can tell it does some crazy stuff in the middle. But remember, when we're looking at limits, we're looking at what does it do as it's going further and further out. So if we look at this graph, it keeps getting smaller and smaller. It looks like it's converging, because it's going down. Definitely doesn't look like in the middle, but as we go further and further out, it looks like it's converging. Now we got to figure out how to come up with that. If I'm looking at the limit of a sine, like a trig function, sometimes that might be a little more complicated to do. So theorem 7 states that if we look at the limit of the inside piece, as long as that function's continuous, I can do that and do the function on the outside of it. So basically what this allows me to do is change this to the sine of the limit as n goes to infinity of pi over n. So I can do the sine of the limit instead of the limit of the sine. Hi, you gotta go. All right. Now, what's the limit as n goes to infinity of pi over and n. That's going to go to 0. And sine of 0 is 0. So that's the limit of this one. Which means it converges at 0. Couple little things before we move on out of these. R to the n power. If you look at R to the n, that is most typically a geometric sequence. It's going to be some value raised to power or an exponential function, which is going to be our geometric series when we look at it in a little bit. They have a very specific case where it converges and diverges. So if we know it's going to be a geometric series or a sequence in this format, we know it's going to converge if the R is between -1 and 1. And we know it's going to diverge if it's outside that point. So if you think about it, that's the difference between exponential decay and exponential growth. Because it's when it's between -1 and 1, it's exponential decay. When it's outside of those, it's exponential growth. So I know it's going to converge between -1 and 1 and diverge outside of that. It'll converge to 0 between those. If it equals 1, 1 raised to any power is always 1. So it's basically a horizontal line. So it converges to 1. So, and we can see that if we look at let's see, A. So you can see whenever A is between okay. Oh, because it oscillates. So whenever it's between 0 and 1, I get my exponential decay. When I have it higher than 1, I get my growth. So that's going to diverge. And if it equals 1, then it's that. When I'm graphing these, if you go negative, remember it's not going to graph it because it's single individual points. Because we're not talking about individual values. Actually, I might be able to change this whole thing. Let's see if I can actually change this. Nope, it still won't. But that's why it converges and diverges in those. All right. One more quick definition. A sequence is called increasing if every value as we go up gets bigger and bigger. It is called decreasing if every value gets smaller and smaller as we go up. It's monotonic if it's either increasing or decreasing. So if it's one of those and always increasing or always decreasing, then it's monotonic. Notice that nowhere in this did it say one is convergent and one is divergent. I can have a sequence that is always increasing and go and actually converge to a value. I can have a function that's always decreasing and it not converge. So those two are two independent things. Okay. Does that make sense? take no answer as a yes. That makes sense. Just because I got a million other things I have to go through in this section. Because they still have to go right into the series. All right. We want to show that this sequence is decreasing. So we've got example 12 over on the side, showing how they did it with a simple number. So I've got 3 over n plus 5 is greater than 3 over n plus 1 plus 5. So basically, we're trying to show that the second value, the n plus 1, is going to be smaller than the first value, the 3 over n plus 5. So, and that's where that piece right there, the a to the n is greater than a to the n plus 1. That means it's decreasing because the second value is smaller than the first value, and so on and so forth down the line. Let's look at this one and figure out if we can decide that. So it says we want to show that this is decreasing. So I've got n over n squared plus 1 is greater than n plus 1 over n plus 1 squared plus 1. That's what so basically there's a question mark there. That's what I'm trying to prove, that that's accurate. Does everybody understand where that came from?
Yeah.
Okay. All right. Now, to solve this one, we're going to cross multiply. So I've got n plus 1 squared plus 1 is greater than n squared plus 1 times n plus 1. Boil all this out, and I get n to the third plus 2n squared plus 2n is greater than n to the third plus n squared plus n plus 1. Cleaning this all up, if I bring everything over to this side, the n's cancel out. I have n squared left plus n is greater than 1. So the question is, when n is greater than or equal to 1, which is when we're looking at our terms, is that always true? Is n squared plus n greater than 1? That would be true. Because I'd have 1 plus 1 is 2, 2 is greater than 1. And any value of n I plug in, that's always going to be true. So since that's true, I know that a to the n is greater than a to the n plus 1. So it's decreasing.
I'm sorry, I'm having a little brain fart moment. Like, can you just explain how it's true again?
You understand how I got to n squared plus n is greater than 1?
No, not really.
So I've got my original problem up top. This is what we're trying to show is true, is that is greater than the second part by just plugging in the n plus 1 for all my n's.
Oh, okay.
So, and then I just, since it's two fractions, cross multiply,
Yep.
and then simplify it down basically. Just did the foiling out and stuff like that. Move everything over to one side, so this way I got to put all my like terms and stuff together. So that's how I got the n squared plus n is greater than 1. Now again, we weren't at that point. We were still trying to show we don't know it's true at that when we're going through and doing the problem. We're trying to show it's true. So by the end, when we get to it, did we come up with something that is always true? Since when we're looking at sequences, n is greater than or equal to 1, it's going to just keep going up because it's terms. I'm not dealing with any negative values and stuff like that. N squared plus n is always greater than 1 for when n is greater than 1. And what I was doing was I was basically showing this part right there, that a to the n is greater than a to the n plus 1.
All right.
The reason why we're trying to show if it's increasing or decreasing is if it's only doing one of those, we have another rule that we can look at. If it's monotonic and it's bounded, it always is convergent. So as long as the sequence only goes in one direction, either goes increases or decreases, and it's bounded, which means there's a value that it never goes higher than or lower than. It is known as a bounded sequence. And if it's bounded and monotonic, then it's convergent. So that gives me the ability to start looking at those things. That's why 1 over n or 1 over x is convergent, because it is monotonic. It's always going down. It's always decreasing. And it's bounded because it'll never be less than 0. So because it's never going to be less than 0 and it's decreasing all the entire time, it's convergent. That's why looking at direction or decreasing or increasing is so important. All right. Any questions before we go into series? Okay. All right. A series. So all a series is a summation of a sequence. So when we're looking at a series, we're going to do a summation of it. So we're adding up all the values in a sequence. And we're going to tell you what it goes to. Now, these can go to infinity, or these can go to a specific value. That's really, again, what we're looking at. Do they converge or do they diverge? So given our sequence, if we look at our partial sums also end up becoming a sequence. So like if we look at the first value, the second value, things like that, they actually can come up to be its own sequence. That's why all the rules and stuff that we just talked about with sequences works, because we can look at the partial sums and make our own sequence to determine if it's going to converge or diverge. So if the sequence is convergent, then the limit of that partial sums equals s, and it exists. If that at number s in the sum of the sequence goes to infinity, then it is divergent. So same concept. If it's going to go to a specific value, it's convergent. If it's going to go to a infinity, then it's divergent. The nice thing is these will go to one of those two. It's either going to go to infinity or it's going to go to a specific value. All right. So let's look at this one. All right. So they gave me a summation. Which is right there. And they're telling me that the sum, so that's what this is here. They're giving me that the sum of that equals this answer at the end. So Sn is 2n over 3n plus 5. So they've done the work for me. They gave me my equation. So I know any partial sum, I can use that equation for it. So in essence, they've given me the equation for the sequence. And they want to know the value. So we can now just take the limit of that and figure out where it converges to. So we're going to look at the limit as n goes to infinity of 2n over 3n plus 5. And just like I was doing with the other ones, this one I can take the whole thing and divide by n. So I have 2 over 3 plus 5 over n. So I have 2 over 3 is what it ends up converging to. Okay. So now this one, they gave me the equation for it. So I didn't have to do any calculations. In essence, they gave me the sequence. So I could just go right to the limits process. They don't always do that though. And one of the major things that you're going to see is the geometric series. So a geometric series is the summation of a to the r, well, with a ratio n minus 1. So a is your initial value. R is the ratio. So R is what's it's each value is going to change by. And then it's always n minus 1 at the top because you basically want to cancel out that ratio. If you look at this piece right here, that R, remember R to the n that we did back in the last one, and we said it converges when it was -1 to R to 1. That's when it converges. And it diverges the other direction. So, and we have when R equals 1. I'll explain why that one doesn't work in a second. And it diverges when R is greater than 1 or R is less than -1. So we originally looked at that for the sequences at the end. Now, if you look at the blue box, it says it's convergent if the absolute value of R is less than 1. Okay, that's that right there is that. That does the same exact thing. So that converges when my ratio is between -1 and 1. It diverges even when it's R equals 1. Who has a good reason why that's the case? Why would it diverge if r equals 1?
Because it's an absolute value, meaning that it could be plus or minus 1.
Nope. What are we doing here? Remember, so unlike the last, we were looking at the sequences, right? We were just looking at that as a sequence, and we wanted to see what that went to. So if r was 1, all the values are 1. So it, in essence, converged to 1. The difference here is we're looking at it as a summation. So if all the values are 1, and I add an infinite number of 1s, I'm going to get to infinity. That's why it diverges at 1 still. So that was our rule for the sequence. The only change is that it diverges at 1 as well, because an infinite number of 1s would still equal infinity. If I have a geometric series, the rule, and if you look in the book at example number 2, it actually goes through and proves this rule to you. I knew I wasn't going to have time to go through and do the whole process out. But basically, that's the rule. So if I have a geometric sequence or series, I know it's going to equal a over 1 minus the ratio. That is what it's going to converge to, as long as r is between -1 and 1. If it's bigger than, if it's outside of that, it's going to diverge and I'm done. So as long as you can get your geometric series so that you know what a is and you know what r is, you can find what it's going to converge to. Notice, without doing any limits, it literally converges directly to that number.
I still don't think I understand how we went from a times r to n minus 1 to a over 1 over.
It's okay. So we didn't. I'm telling you. It's not. So this value, actually, you know what? We're going to do it. We're going to do a problem. And I think, so I think you're looking at it and say, okay, how does that equal that? It's that sum. If we added every single value all the way out to infinity, that answer is going to converge to a over 1 minus r. So it ends up converging out to that value. So it's just like we were looking for at the limits and stuff before. That's what it's going to. So the next problem we were going to do actually was doing that. So let's actually do it. So here we've got our geometric series. Let's find my equation for it. So remember, we're looking at, it's the summation of n goes to, or n1 to infinity. And it's a r to the n minus 1. So I need to know a, and I need to know r. So in this problem, my a is 5. That's my initial value. Now I need to figure out what my r is. So what am I multiplying by to get to the next one? And in this situation, I'm multiplying by -2/3. Does everybody see where I got the 5 and the -2/3 from?
Five is your start.
Yep. And then if I multiply that by -2/3, I get 10 over 3, or -10 over 3. And if I multiply that by -2/3, I get 20 over 9. So my equation is that. That is the series that will produce that equation. That's the summation. Now, if we look at the graph for that, if I graph those points, what do you notice is happening with those dots? It looks like it's converging. Huh? Yeah, it's converging. The question is what is it converging to? That's where that equation that we had, that A over 1 minus R, that gives me that conversion point. So A is 5 over 1 minus negative 2 over 3. So this is 5 over 5/3, which equals 3. So it converges to 3. So if I was to add all those values all the way out to infinity, I would get 3. Does that make sense? As we're going, almost all of chapter 11 is just going to give us more and more ways to look at functions and look at series to determine if they're convergent or divergent. That's in essence all we're doing. And if they're convergent, we're going to have ways to be able to find those values. This is just one of those ways. This function right here, that piece right there, is just one of the ways. If I know it's a geometric series, as long as the ratio is less than 1, the absolute value of the ratio is less than 1, I know it converges, and it converges directly to that point, that equation right there, A over 1 minus R. I don't need to do limits for it. I just need to make sure that it fits this criteria and it converges. Not every one of them is going to be this simple. All right, let's look at another one. All right. So this one, what makes this one more complicated actually is less to do with figuring out if it's convergent or divergent. It's that we have to do some algebra to manipulate this problem to make it work. So we can figure out if it's because this is a geometric series. It's just not in a format that's going to help me figure it out. So we need to manipulate it. So I'm just going to look at 2 to the n and 3 1 minus n. I'm going to ignore the summation symbol for a little bit while we're going through and doing the manipulation. All right, so remember, my goal is to get it to look like this. That's my goal. I want one number in front, I want one ratio, and I want n minus 1 up on top. So, do we have anything that looks like an n minus 1 in this problem right now?
The exponent.
Yeah, we have that right there, right?
Yeah.
But it's backwards. So, if I do this, is that the same thing?
Yes.
Okay. Now, what do negative exponents, how can I get rid of a negative exponent? I can put it down the bottom. Because I don't want the negative sign there either. I want that gone. But by having the negative sign gone, I could, if I move it to the bottom, now it's gone. Okay. Now we've somehow got to get this fixed up here. So this is the same thing as saying that. Because I could do 2 squared, which is 4 to the n. Because in essence, if that right there is just 2 squared to the n power from your exponent rules, remember? Does that part make sense? All right. But I still got to get that to be n minus 1. So this is probably the hardest and most confusing part. Okay. So that's that. All right. So that's 4 to the first power, right? And if I had 4 to the n minus 1. Remember when we put things together, we add exponents? So that's still the same thing as saying 4 to the n, right? Does that part make sense?
Yeah.
So the last step is put the n minus 1s together. So I have my, this is now my A, and that's my R. So does this converge or diverge? R equals 4/3, right? Is that less than 1 or greater than 1?
Greater.
So that means divergence. Because it's got to be less than 1 to converge.
So in this case, we don't need to do the A divided by 1 minus R because R is already bigger.
It's going to infinity. The only time we have to do the A over 1 minus R is when we're looking for the value it converges to. Since this doesn't converge, I can't do that. Just because I really like this problem. And we haven't done a word problem yet, so. All right, be honest. When your doctor tells you to take your medication, do you always take your medication exactly as prescribed by the doctor? And do you always take it till he tells you to stop taking it? Probably not. There's actually a real reason that they actually do that. So like when you're taking antibiotics and stuff like that, when you take it, they tell you to take it same time every day. until you complete it out. Because when you're looking at a drug, when you take the initial medication, it spikes up to that value. When you take the next time, the drug isn't completely out of your system yet. So it's going to, that value actually increases over time, and it actually goes to a specific value. It converges. The convergence value that they're looking for is what they actually are prescribing you to take. So when you're getting 10 milligrams, or in this case, 0.2 milligrams, that's not actually how much drug you need in your system to kill the virus or be healthy or whatever else you're taking it for. You actually need the value that it converges to in your system. That's why it's always important to take your drugs on time and continuously until you're told to stop. So let's actually look at this, and we're going to come up with the equation, and then we're going to figure out what it actually converges to. Because that concentration level is actually the most important part when they're prescribing you drugs. So the drug is administered. You're administering 0.2 milligrams per milliliter, so 0.2. And before the injection, 30% of the drug remains in your system. So on day 0, so actually we can do this one. So Cn plus 1, we have the 0.2, and then we have the 0.3 of whatever the value before that one was. So that's my sequence that I'm looking at. So let's come up with some values. So C0, so day 0, you have 0.2. Oh, sorry, day 0, you have 0. Day 1, you have 0.2, correct? Does that make sense? So the first time you're getting it, you have 0.2 milligrams in your system. Day 2, you have 0.2 plus of C1, which is 0.2. Does everybody see where that's coming from? Because remember, our goal is we're trying to come up with an equation for this. And the first question was they want to know how much is in your system after 3 days. So on day 1, I have 0.2. On day 2, I have 0.2 plus the 0.3, the 3%, the 30% that's left, which would be, in this case, 0.26. On day 3, we're injecting a new set there. And then I have of this part here. So 0.2. So that goes there. That goes there. So it's building on itself because that stuff's still in my system. Does that make sense? Or no? But remember, the series is whatever the one previous to it, we're multiplying by 0.3, and we're adding the 0.2 to it. And that's in essence what we're doing. We're taking the 0.2, we're multiplying it to 30%, and we're adding the 0.2 back to it. And then it just keeps compounding on itself. So after 3 days, there's 0.278 milligrams of the drug in your system.
Hey, Professor, I'm a little confused here. So on day 2, that's easy, 0.26, true, that makes sense. And see, on day 3, it would be 0.2 times or plus 0.3 times day 2, which was 0.26, correct?
Right.
Right, so 0.26. Oh God, never mind. I put 0.3. I'm sorry. Never mind. I'm good.
Yeah, it's basically that blue is the 0.26. So there's a reason I'm writing it out like this though, because remember, the next piece is we want to find out the equation so I can find out any day. We want to go to the nth power or the nth term, and without having to write it all out. So I'm going to make one little change to how C3 is written. There's 0.2 plus 0.3 times 0.2 plus 0.3 squared times 0.2. So notice how the 0.3 is the one being raised to the power. And the 0.2 is just continuously being added to it. So C to the n ends up being the 0.2, 0.3 to the n minus 1. So it just basically, we're going to continue going until that is at the end. So this is a geometric series with A being 0.2 and R being 0.3.
I don't understand where you made the jump to square
Because I have, if I'm just distributing this, I have the 0.3 times 0.2, which is that one. And then I have 0.3 times 0.3, which is where I get the 0.3 squared.
it. Got it.
And if we kept going, it in essence ends up being, because if you think about it, this is the third one and I only have squared. That's where I got the n minus 1 from. So my geometric sequence or series. So n equals 1 to infinity, 0.2 and 0.3 to the n minus 1 power. All right, so does this converge?
Your R is between 1 and -1, so yes.
So it converges. So now we can figure out what it converges to. And remember, it converges to A over 1 minus R. So that's 0.2 over 0.7. So it converges to 2 sevens, which is 0.286 approximately. So after a certain amount of time, you're getting closer and closer to 0.286 concentration in your bloodstream and not the 0.2 you're putting in every night. However, the only way that works is if you take it the same time every day. Because if you take it at different times, that 30% changes of what's left in your bloodstream when you take the next dose. So that's where that changes. All right. Hold on. All right. So we want to look and see if this one's convergent or divergent. First off, is this one a geometric series? No, it is not. So if we're looking at a series like this that's not a geometric series, sometimes we just have to go back to looking at the partial series and see what they actually come out to be. So this series right here, if I'm looking at it, would be 1/2 plus 1/6 plus 1/12 plus, and it just keeps going. So looking at this, it might converge, it might not. So we're gonna have to do a little bit of work to figure out if it's gonna converge or not. Looking at this right here, thinking back to what we did with in chapter 7, one of the things we covered was partial fractions. So 1/n plus 1, I can change to 1/n plus 1/n plus 1. Oh, not plus, minus, sorry. Minus. No, I'm not going through and doing the partial fractions all out to get that in, to show you how it came out to be. Trust me, that works. All right, so here's why we did that. Because now that I'm adding and subtracting, I'm going to be able to cancel stuff out. So if we look at this as a sum of values, so my first value is going to be 1/1 minus 1/2, which gives you 1/2, correct? The next one is going to be 1/2 minus 1/3. The next one's going to be 1/3 minus 1/4. Plus, and it keeps going. So eventually it's 1/n minus 1/n minus 1. Does everybody see where I was getting those values from? I'm just plugging in the first number, the second number, and just keep going forward. So that's term 1, that's term 2, that's term 3, so on and so forth.
Do you mean to put -1 or +1?
Where,
At the end, it's in 1 over n minus 1 over n. Oh, I'm good. I understand. I think.
yeah, that was +1, yeah. All right, so now if we look at this part right here, I have a -1/2 and a +1/2. Right? I have a -1/3 and a +1/3. And if I continue this, I'd have a -1/4 and a +1/4. And I'd have a -1 over n and a +1 over n. So this whole process goes down to 1 minus 1 over n minus 1. So if I look at the limit as that n goes to infinity, I get 1 minus 0, which is 1. So the series converges to 1. So you can see here, that's the partial sums, and it's getting closer and closer to 1. AN is that value in there. As those values are getting, so that's the 1/2, the 1/6, the 1/12. They're getting closer and closer to 0. Right? All right. This one's actually a very, very important series. The harmonic series. And one we're going to come back to a couple times. Looking at that series, do you think it's convergent or divergent? I know what it says, but just looking at it, do you think it would converge or diverge?
Converge.
Right, because those fractions are getting smaller and smaller, right? And if I was to graph it, it'd be going down. The problem with the harmonic series is that it does get smaller and smaller. It just doesn't get smaller and smaller fast enough to converge. And I'm not writing all this out, so I'm literally going to copy and paste it because it's a ton of writing. So, but I'm going to explain. All right. All right, so again, we're going to look at it in terms of partial series. We're not going to do every one on purpose. So they looked at the first one as S2. So they're just looking at the first 2 terms. So you get 1 plus a half. Okay. So 1 plus a half would be 3 over 2. So 3 halves. The fourth one would be 1 plus 1/2 plus 1/3 plus 1/4, correct? That's the first 4 terms. This is where they do something crazy. They're saying, well, that's bigger than 1 plus a half plus a fourth plus a fourth. Is that true?
Yes, because the 1/3 is bigger than the 1/4.
Right. That's actually the most important part of this whole thing. Because now it's 1 plus 1, that becomes 2. So I know that S4 is greater than 2. I don't care how much greater. I just know it's greater than 2. Then they go to S, then they do the first 8 terms, and they do the same thing again. And what happens is this is going to be greater than 2.5. And then the next one is going to be greater than 3. So notice how each of those values, that number is continuously going up. All right, it's literally going up by 1/2 every time. And it's going to keep going up by 1/2. So the 32nd one I know is greater than 3.5. And the 64th one I know is greater than 4. And it ends up being that the highest one is greater than 1 over n plus 2, or n over 2, depending on whatever the n value is. So that's going to get increasingly higher. It's not going to get smaller and smaller. That's why it's divergent. So the thing that you want to come out of this is that this series, a harmonic series, 1 over n, diverges. Always. Okay? Even though it looks like it would converge, even though you would assume it would converge, it is divergent. All right? And that's going to lead into the next piece, which is the next two things. We're almost done, I swear. All right. If the series is convergent, then my limit of the limit of the an equals 0. So if my series, if the limit is convergent, then my limit of an equals 0. Okay. The opposite, or the converse of that, is not true. All right. I can't say if the limit of an equals 0, then the series is convergent. That is not true. And it's not true because of this, the harmonic series. Because what's the limit of n goes to infinity of 1 over n? 0. But this diverges. So this direction is true. If the series is convergent, then I know that limit has to be 0. But the converse is not true. So you can't just reverse those to help you out. The test for divergence is another piece of information. The test of divergence says if the limit of a to the n does not exist, or if the limit of a to the n is not equal to 0, the series is divergent. So if the limit does not exist, or equals anything other than 0, the series is divergent. Notice, nowhere has this said if the limit of it equals 0, it's convergent. We still don't know that. We do know that if it's not 0, it is divergent. Does that make sense? All right, we're going to do one of those problems and then we're done. All right, so I want to show that this diverges. So if it diverges, I can do my test for divergence. All I need to figure out is that the limit of this, what the limit of this is. If it doesn't equal 0, I know it diverges. So I'm looking for the limit of n squared over 5n squared plus 4. What am I going to divide everything by in this problem?
N squared.
Yeah. As long as I divide it by the same thing, it doesn't matter what I divide it by. It's just, it'll still come out to be the same thing. Again, your goal is to get rid of stuff. In this case, the n squared is going to get rid of stuff. So I have the limit as n goes to infinity of 1 over 5 plus 4 over n squared, which is 1/5. So since 1/5 does not equal 0, it diverges. That's what the test of divergence shows. If that does not equal 0, the limit of that does not equal 0, it diverges.
It does not mean that it converges.
It does not mean that it converges. Even if it equals 0, we have to do something else to figure out if it converges. Okay. So if you do it and it comes out to be 0, we need to use some other rule to determine if it's convergent or not. However, if it's not 0, we know it diverges. So the test for divergence is one of the first things to try a lot of times because it'll eliminate quite a bit of problems. If it comes out to be 0, we go something else. But if it doesn't come out to be 0, we know it diverges and we're done. We can move on. All right, that is it.